Okay, welcome to your very first lesson in chemistry, and it's going to feel like we're in a math class right now for the first few units here. And we're going to talk about calculations in chemistry. This very first topic here is going to sound a little morbid, but this is really just a rule of thumb that if you are writing some numbers, and let's say you're a doctor and you're prescribing heparin, for example, and this is a true story, this is what has actually happened, that prescribing it, maybe he writes it like this, and I'm not even sure if you guys can see what I just did there, but it should look like 0.5 cc's, so half of a cubic centimeter. But you can probably guess what's happened is that by the time the nurses look at this in duplicate or triplicate, they might read it as just 5 cubic centimeters. So what we want to do is, if you ever have a decimal in there as your first starting point, go ahead and put a 0 in front of that. So 0.5 cc's is a much better way to phrase that. Then there's no mistaking that that should be half of a cubic centimeter instead of 5 cubic centimeters. And that was something that happened, I think it was in New York. Heparin is a blood thinner, and there were apparently quite a few deaths that happened from that. So we don't want that in chemistry. Okay, we are going to move on, and our main calculations that we're going to talk about today are, we're going to get into talking about something known as significant figures, and then also how to use those in some calculations, and also how to use scientific notation. For this, you're going to find that you do want a calculator, but we will get to that here shortly. So before we jump into that, let's make sure we understand the difference between accuracy and precision. And hopefully you're following along with your notes, and you see that there's a great little place for you to fill this stuff in. Accuracy is how close a measured value is to an accepted value. So if I were to say, hey, the lifespan of a squirrel is 9 years, in order for me to know whether or not that's accurate or not, I would obviously have to know what the lifespan of a squirrel is. So I really couldn't answer that without knowing that the actual value of that. But what we're going to do is we're going to be able to compare values that we calculate with the accurate values. And then we get into precision. Precision has to do with how close a series of measurements are to one another. So let's say we're playing darts, and I hit all 3 of my darts right there in that bullseye. Yes, I am very accurate because that was the accepted range or value of what I wanted, but I was also very precise because all 3 of those were in that same location, so they were all close to one another. However, if you hit 1 over here, 1 over here, and 1 on the target, obviously that would not be very precise. Now, when this comes to using some equipment, what we're going to see is that we've got different pieces of equipment in the laboratory that we're going to be using, and we're going to always try and choose what is most precise for that experiment or for what it is that we're trying to measure. So, for example, a beaker is not going to be an instrument, a piece of equipment that we're going to use to measure the volume of a liquid. Instead, we're going to use what's known as a graduated cylinder, and the reason being, hopefully you can see this, that there are a lot more little tick marks in there. So you get greater number of increments, so you get greater precision. And when we start talking about different types of numbers, we see that there's a couple different types. You can have exact numbers, and you can have inexact numbers. So an exact number is going to be something that does not affect our significant figures. And that'll make more sense once we start talking about sig figs. But it does not affect the number of digits that we use to report our values or answers in. And these tend to be things like counts. So if you have exactly 12 eggs in a dozen, then that's just a count. Or when we start talking about conversion factors, 1 meter is exactly the same thing as 100 centimeters. So we're never going to let these exact numbers limit our number of digits that we use when we report our answers. What we will be using is those inexact numbers, and those are going to be the measured values. When you're reading through a word problem, it's just going to be what's given to you in there, things that are not counts and that are not conversion factors. So The thing about these values is that they convey the quality of the measurement. So it has to do with the quality of that measuring device. And so what we'll be able to do is we'll be able to control the number of digits when reporting these values to ensure that that measurement does not appear to be more or less precise than that equipment actually allows that measurement to be. So for example, if you're using a 10 milliliter graduated cylinder, you might be able to look at the increments on the side of that graduated cylinder, and if we were in class, I would show you this right now. But you would be able to get it out to 3 significant figures, in other words, to the hundredths place with those milliliters. However, a 100 milliliter graduated cylinder, you would only be able to measure out to the tenths place, to the 1 digit past that decimal. So it is less precise than if you used something that measured out to the 100th place. All right, so now it's time we get into what significant figures are. And by the way, these are going to stick with us all year long. This is going to be something we constantly refer to as sig figs. And what they are the numbers in a measurement that include all of the digits that are known plus a last digit that is estimated. And by the way this video works is you can go ahead and pause this as you need to fill things in. But I'll repeat that. It's the numbers in a measurement that include all of the digits that are known plus a last digit that is estimated. And before we get into how we actually calculate them, let's think about why we even care. Why do we use this? And this guy right here, you guys are a little young now maybe to remember the first Olympics that he swam in. But if you might be able to remember it, that what he ended up doing was he won by 1/100th of a second. So he won by 0.01 seconds. He beat his opponent. And before that, prior to 1972, the Olympic events were only measured in tenths of seconds. So what that would have meant is that, hey, he wouldn't have necessarily been a winner. There would have been a tie. And so in this case, we can see that going out, we've got a precision of the hundredths place, and I'd have to know what's going on up here to be able to count those sig figs. But this is more precise than if it just went out to the tenths place. There's a couple other kind of interesting things. Let me see a slide in here for it. Yeah, why when we can measure time to the millionth of a second, so we actually have equipment that's even more precise. Why do we only measure swimming events to the hundredth of a second? And what happens there is we've got some constraints with swimming pools, and the swimming pools themselves, when you start thinking about the distance that the length of a pool, they can vary not only from pool to pool, but from lane to lane. So that's kind of interesting. And so that's just a way of not giving any benefit to an extra lane. So that's why we only measure out to the hundredths. Okay, so here are some examples that you do not have on your notes, and I'll try and go through these kind of quickly. But here it says, what distances can you be certain of on the ruler in Model 1? So here's what we have. We have this piece of metal, let's say, and we're trying to measure that length. Well, all I can really tell you is that the length is going to be greater than 0 centimeters, but it's going to be less than 10 centimeters. So I do not have a known digit, but by estimating, I can come up with an estimated digit. And if you go back to what we just said about significant figures, it's the numbers in a measurement that include all of the digits that are known plus a last digit that is estimated. That is going to be my 1 sig fig that I've got in here. And I don't know what to call that. Let's say it's 3 centimeters. That's my estimated digit. Well, now I have a little bit more precise piece of equipment. And sure enough, that 3 right there, that is a known digit, that 3, but now I can go ahead and estimate another digit in there. Maybe I'll call it 3.2. So that 2 is my estimated digit in there. So in this case, I can measure it out to 2 significant figures. Ooh, it's even more precise now. I see that not only is it 3 centimeters, but when I look closely, and I'm afraid if I draw on this, I'm just going to make this messy, but let's say it's not only 3.2, I can see it's greater than 0.2 but less than 0.3. So now I'm going to eyeball that and just say, oh, I don't know, let's call it 3.21 centimeters. So you can see that we've got those two digits that are known plus a last digit that is estimated. So here we have three significant figures. So here's another little question here. It says, out of these guys, which of these are actually valid measurements and why? So it would have to be 3.21, 3.20, 3.22. The others are not valid because here Marks has too few sig figs and Emily and Dion are making up significant figures. There's no way that they can be that precise with that piece of equipment. So we see that with this model, we have two digits that are known and then one that is estimated. All right, so now we get to our rules for counting significant figures, and you do have these rules on your notes. You're going to want to make sure that you understand these. I happen to have a couple examples with mine that are not listed with yours, but here the first one, and hopefully as we go through these, just think about them. They should make sense to you. Here it says all non-zero numbers are significant. So if you have a number like 451, every single one of those is some sort of measured value. They are significant digits. Same with 56.1. There are no zeros in there. Every single digit is significant. Decimal points don't matter at all, but all of those are going to be significant. Now, if you happen to have zeros in there, but they are sandwich zeros, then they are significant. A zero is very much a measured value, just like a 1 or a 2 or a 5 is. So in this case, we see, for example, that 706, because that 0 is in between two other non-zero numbers, there's no question about it. It is going to be significant. So you've got three significant figures there. Here you have 5, here you have 5 as well. So again, the decimal points don't really play a role because those are sandwich zeros. So these two, we usually don't have people have mistakes with those. Those are usually pretty straightforward. Now we get into some leading zeros. And the thing about these is that they're never going to be significant. All they are placeholders. So let's say you have something like 0.382, and that's how many kilometers you have. Well, there's three significant figures, which, by the way, is exactly the same thing as saying 382 meters. It is still three significant figures. There's absolutely no difference between that. Just going from meters to kilometers, you don't suddenly make it more precise and count that as a significant figure. That is not included as being significant. It is just a placeholder. So again, that's when it's a leading zero. Then we get into trailing zeros. This is when you have to really think about it a little bit more. Trailing zeros are significant if the decimal point is present. So for example, if you have 67.0 in that first one, this 0 is that last estimated digit. Remember the definition for significant figures. That is the estimated digit. We know the 6 and 7, and the 0 is estimated. Maybe it was close to a 0.1 or a 0.2. Here it happened to be right at a 0.0, so that is a significant number. If you just had 67, then that is two significant figures. You don't have equipment that is precise enough to measure to the tenths place and be able to get that last digit there. So the zeros are significant if the decimal point is present. If they are not present, if a decimal point's not present, then it is not significant. So again, let's look at the difference here. We've got our 500. If it says 500, that means there's really only one digit that is known, or maybe it's estimated, I guess I should say. Whereas if it's 500 with a decimal point, in that case, you have three significant figures. So this is one significant figure, This is 3 significant figures. Just have to think about that as we go through them. And then finally, the exact numbers, like we said, they're counts. So if I were to be in a classroom and see 26 students, I have exactly 26.00000000. It's an infinite number. There's not going to be a fraction of those. So counts have as many significant figures as are needed. In other words, they do not limit the calculations, because we're going to see that it's the significant figures that limit how we report our answers. Okay, so now we're going to determine the number of significant figures in each of the following quantities. And by the way, what that means is that not only are we looking at numbers, but we are also looking at units. And that's what it means when it says quantities, numbers and units. And we refer to both of those a lot in chemistry. All right, that first one, it says 3.82 liters. So in that case, should be pretty straightforward. There are no zeros. Yeah, we got a decimal point in there, but who cares? There are no zeros. Every single digit is significant. So we have 3 sig figs. Moving across to the right, 24 meters. Looks like 2 sig figs. Ooh, now we've got some zeros in here. This 0.0619 kilograms. So in this case, I look and I see that my zeros are leading zeros. They are just placeholders. That's all that is. So if I were to think about that in terms of grams, that's the same thing as 61.9 grams. So none of those are going to be significant. So the zeros, I'm sorry, the other numbers, the 619, are significant. So we have 3 significant figures there. Now, near the end of this lesson, we are going to talk about scientific notation. And you probably have a little bit of an understanding about scientific notation already. But we see that 2.1 times 10 to the 4th grams, because that exponent is positive, that means it's a really big number. So that decimal point goes to the right 4 places, and it's the same thing as saying 21,000 grams. So if we look at it here, you can see there are 2 significant figures. But guess what? It's really even easier to look at it from scientific notation, because this right here, known as the coefficient in front of that times 10 to the 4th, which we don't really care about that part for sig fig calculations, that 2.1, that coefficient tells us that there are 2 significant figures. So it's really easy to look at that and see. Okay, the next one. We have 3.4610, we have a 0 in there, but there is a decimal point present. So because that decimal point is present, that 0 is significant. So there are 5 significant figures. But in the next one, yeah, we've got some trailing zeros as well, but there's no decimal point. So those are just thrown in there as well. They're not significant measured values. So in that case, we only have 3 significant figures. Okay, so now this one, yes, you have this on your paper. It says what measuring device is used in the picture to the right. This is known as a graduated cylinder, something that hopefully you guys will become familiar with quickly. Some of our equipment that we use. There's a graduated cylinder, and it says how should you record the volume of the liquid and how many significant figures did you report? Well, if we look at our close-up value or view here, I see that it is definitely greater than 40 and less than 50. Well, not only that, I see that it's greater, if I count these increments, I see that they're by ones. You're looking at the bottom of that meniscus when you get at eye level. And I see that, yeah, it's definitely, I'm going to say greater than the 43. It's less than the 44. But in fact, I'm going to say it is right on the 43. In fact, I can go ahead and estimate that one last digit, because you should definitely be able to say the measured value of the 4 and the 3, it's that estimated value to the 10th place. So in this case, we have 3 significant figures. Hopefully that made sense. You've got 2 known digits and 1 estimated. Okay, here we have a piece of equipment. It says, what values in centimeters would you record for measurements A, B, and C? For A, we've got centimeters that are marked. Here's 1 centimeter. So here's 0.567. I'm going to say I've got 0.7 centimeters. Well, that's a known, but I can also estimate a digit, and it's going to be 0 is the way I'm going to estimate that. Maybe someone else would say 0.71. Either of those would be fine. Maybe it is closer to 7.1. It's hard to tell. Okay, all of these are going to be in centimeters. I don't really have much room to write that, but I like you getting into the habit of writing those units. Okay, the next one, B. Well, it's greater than 1. I see that it hits that 1.5, but I need to throw in my estimated digit as well. So I'm going to say 1.50 again in that case. And with C, I see that it's greater than 2 centimeters, so I'm going to say 2. There's 5, 6, 7, 8. I know it's greater than that 0.8, but less than the 0.9. So I don't know, let's call it 2.83, somewhere in there. Okay, if we think about significant figures, A has 2 significant figures, where B and C each have 3 significant figures. But really what we notice here is that they're all measured to the hundredths place with this piece of equipment. Okay, rules for rounding. This is probably just what you would normally do. So these are our typical rules, and you should know this. That if it's a number between 0 and 4, you just leave it alone. But if it's 5 or greater, 5 through 9, you raise it. So if you have this value right here, this is our number that we're going to start with, and we want to round it to 2 significant figures. Well, if I were in front of you right now, I'd take my hand and cover up most of those digits. So I would cover up all of the digits except 21.4. So that's what I would be looking at. So you're going to cover up everything but 2 digits plus 1. Since I'm looking for 2, I always want to keep that extra 1 to determine how to round it. So 21.4, my rules tell me that I'm going to round it just to 21, because the 4 means leave it alone. Well, if I want to round it to 3 significant figures, now all I'm doing is looking at the 21.40. So for 3 significant figures, that 0 again means leave it alone, so it's going to be 21.4. 4 significant figures, now I'm looking at the 21.409. So if I want 4 significant figures, it's going to be 21.4. Well, now I look and I see that that 9 is going to cause that 0 to raise up to a 1. So 21.41. I'm going to keep going with this idea. Here we have a 6 there, but I'm going to round it to 5 sig figs. It is 21.4. We know that it's going to be a 1, but that 6, and maybe I should have backed up, that 6 is going to round up that 9 to a 10, which makes it that 1, 0. So make sure you stop and think about that one for a little bit. Okay, if we want to round it to 6 sig figs, I have to throw in another digit. I'm going to throw in a 5. And in this case, it's going to be 21.4097. That 5 causes that 6 to round up. And then finally, I'm looking at all of them, and I'm going to round it to 7 sig figs, and it becomes 21.40965. There we go. All right. So in the next example, what we're doing is we're rounding to 4 significant figures every single time. Here we happen to have something that's in scientific notation. All you're doing is thinking about the coefficient in front. So in this case, it's going to be 4.00. Well, what am I going to do? That last 0, because there's a 5 after it, it's going to raise up to a 1. But that's not good enough. Please do not forget to add in the times 10 to the 5th. That's going to be an important part. I'm not very good at writing with a stylus on this, so my writing is a little messy. Hopefully you can see that's an exponent. Okay, next one, we've got 3, 7, 5, and now point. Now we need to figure out what to do with that 6, and there's a 5 behind it, so it is going to round up to a 7. And then lastly, these, I kind of like these because I see a lot of people that make mistakes on these, and I want to make sure that you guys don't fall into that little trap. So to round it to 4 sig figs, it might be tempting to go, okay, well, it's going to be 8, 9, 7, 6. Done. But that's not the case. There's 89,000 is completely different. Actually, I didn't even say that right. That's 89,762,334. Completely different number than 8,976. So don't forget to throw in all of those additional insignificant zeros in that case. So that's going to be really important. Now keep in mind, I did not put a decimal point in there. If you add a decimal point to that, they then become significant, so you have more than your 4 sig figs. So just keep it as is like that. Okay, now we get to our calculations with some sig figs. And I don't know if I need to read through all of this, but really what we see is that when we go through these calculations and we report our answer, what we want to do is we want to base it on the least precise number of sig figs, or least precise number in your calculation. Just like the weakest link of a chain, you can't have an answer that's more precise than that least precise number used to get that answer. So when we go through this, you're going to notice that we have completely different rules between addition and subtraction and multiplication division. There's 2 different sets of rules. And then another thing that's worth noting, and I just went ahead and threw it in here, in chemistry, we do not use fractions very often. It is very, very rare that we use fractions. We're going to use decimals instead. So if you take something like 10 and divide it by 3, the answer is 3.3. It is not 3 1/3. Okay, so now we're getting to our rules for calculations. And what we're going to do is we're going to start with talking about multiplication and division, and then we'll look at addition and subtraction. And our rules for multiplication and division, it tells you some rules here. I'm going to see if I can write this in here. But I'm going to rewrite this. I'm going to say that our rules are to round to the least number of sig figs in your given problem. Ooh, that's sloppy. Okay, so round to the least number of sig figs in your given problem. Those are the rules that you're going to follow. So for example, if you were to plug this in your calculator and you take that 13.1 times 1.2039, your calculator would spit out this big long answer. Well, if you look closely at the numbers that you started with, this first number, you've got 3 significant figures. 13.1 is 3 sig figs, and in the second one you've got 5 significant figures. So what you need to do is you need to take that answer that is in your calculator, because your calculator's smart, but it's not that smart. You need to take it and you need to round it to 3 significant figures, because that is the least number of sig figs in your given problem. So those are the rules that we're sticking with. So when you take your 15.77109 and round it to 3 sig figs, your answer is 15.8. So hopefully that made sense to you. When we do calculations, by far the majority of the time we're doing multiplication and division. What I would recommend to you guys, and I know that people will continue to ask this throughout the year, but what you'll see when I do these is if you have a multi-step calculation, which we quite often do, I would just keep going in your calculator and then report that final answer at the end. So what I have listed here is keep at least 1 more sig fig in your intermediate results. So in other words, if you stop and actually write it down, add more sig figs at that point, and then round at the very end is usually a better way to do it. I like to just keep as much as I can in my calculator and write it down once. Okay, now we're moving on to addition and subtraction, and there's actually different rules here. You're not going to round to the least number of sig figs in the problem. Instead, you are going to round to the least number of digits past the decimal in your given problem. Round to the least number of digits past the decimal in your given problem. So here's our problem that we've got. 350.04 plus 720. You notice that you've got 2 digits past the decimal, and in the second one you've got 0 digits past the decimal. So even though your calculator gives you this answer of 1070.04, you need to round it to the least number of digits past the decimal, which would just be a whole number of 1070. All right, so probably would be good practice if you guys were to throw these in your calculator at some point and make sure that you could come up with these actual answers. In fact, well, let me just start by saying with this one right here, this first example, if you were to take all of that in your calculator and throw it in, you'd get that 0.01699021. Now, in order to get that answer, make sure, and I'm just gonna, I guess, spell it out here. I would punch into my calculator 239.1 times 46.23 times 0.0029 divided by 16.508 divided by 114.29. If you say times, it's going to throw it into the numerator unless you used parentheses. And I grew up in a time when we didn't have parentheses on our calculator, so I just hit times when it's in the numerator and divided by when it's in the denominator. So plug that into your calculator. Make sure you get this answer. Now what you need to do is you need to figure out how to round that. Well, this is all multiplication and division, so I would look at this and say, okay, well, 239.1, there are 4 sig figs. This next number has 4 sig figs. The next number has 3 sig figs, just that 290. Then we have 5 sig figs and 5 sig figs. So based on that information that you're starting with, you need to round your final answer to 3 significant figures because that's the least number of sig figs, least number given to you in your problem. So when we round that to 3 sig figs, it becomes 0.0170. So notice that the 9 bumped up the previous 9, which bumped up the 7 as well. So that's what we end up getting there. Okay. Next one, you plug this into your calculator. This is what your calculator gives you. So you have 4 sig figs and 3 sig figs. So you need to round your answer to 3 significant figures. 2, 6, 5. Not good enough. Need to throw in a couple insignificant zeros as well. So 26500. All right, that's our multiplication and division. Notice now that we have a different set of mathematical functions that we're using. We're using addition and subtraction in the next few. So what I want to do is count the number of digits past the decimal. Here we have 2 digits past the decimal. Here we have 1, here we have 4, here we have 2. So based on that, we need to round our answer to 1 digit past the decimal, so it becomes 10206.5. And finally, go through that same thought process, and you should get 42.36 on the next one. Okay, so now what we're going to do, we're going to finish this up with some scientific notation. This is going to go pretty quickly. I'm hoping that you guys have some background in this. We're not going to learn a lot of the stuff that you would necessarily learn in a math class. We are calculator people. One of the main focuses is learning how to plug this into our calculator, and unfortunately it's going to be hard for me to do this in a video. If you're sitting in class, we would be able to work through this a little bit easier. But what we want to do, if you're changing this to scientific or exponential notation, same exact thing. We always need to have our decimal be behind the first non-zero digit. In other words, it needs to be a coefficient. This is not working. Coefficient must be between 1 and less than 10. So you're never going to have 2 digits before your decimal. It's always just going to be 1 digit. And then you can count the number of places that decimal was moved. Really, the easiest thing to think about here is that if it's a really big number, it's going to be a positive exponent. If it's a small number, it's going to be a negative exponent. Okay, so if we were to write this number in scientific notation or exponential notation, same thing, I need to write my coefficient as a number between 1 and less than 10. So 6.74 times 10 to the, well, this is a really, really small number. So it's going to be a negative value. And you just count the number of places that you had to move that decimal in order to get it there. And it was 8 places. So 6.74 times 10 to the negative 8th. Notice that here I've got 3 sig figs, and here I've got 3 sig figs based on those rules. These zeros are just placeholders. So if you're thinking in terms of sig figs, notice that just changing it from standard notation to scientific notation would never change your number of sig figs. Okay, next one. These become a little bit more challenging. The way I like to think about working through something like this. Here it says rewrite the number in standard scientific notation. This might at first glance look like scientific notation, but notice that your coefficient is not between 1 and 10, less than 10. So what I like to do is I like to, even if I don't write it down, and just for learning purposes, I'm going to write this down right now, but I like to change it over to standard notation first and then put it back into the correct scientific notation. So if it says to the negative 9th, we need to make it even smaller, right? We need to move that decimal point 9 places to the left. So when you move it 9 places to the left, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, plus these 3 zeros, 3, 7, 8. So that's what it would look like in standard notation. Now what you're doing is you're taking that and putting it into scientific notation, the correct way, which would be 3.78 times 10 to the, well, you could just recount those zeros. Now I know a lot of you guys are not going to go through that process that I just went through. There's an easier way to do it. You could probably just take these 3 zeros and add it to that 9 and go one more. I realize that you guys can work through that, but this would be a fail-proof way of going through it, is if you work through it the long way. So 3.78 times 10 to the negative 13th would be the answer. All right, almost done here. Last little bit, and again, this is the focus of this should really be how to enter it into your calculator. So make sure you get with a friend or come and see me and understand how to plug it in. But when you are, I'm not even going to go through this stuff. That's the math side of it. We want to think about how to get this into your calculator. So we've got a set of examples here. If you're going to plug this into your calculator, what I would do, I would say you've got 9.6 times 10 to the negative 4th. So in my calculator, this would be so much easier in class to see this, but here we go. 9.6, and then you hit your, you have 9.6 is what you would punch in. Then you hit the second function key, which is this little blue key right here. And by doing that, then you're going to hit the comma, which is the same as raising it because you hit the second function key to the exponential notation of. So that's like saying times 10 to the, and then you hit your negative sign, which is right here. Make sure you don't hit the minus, but the negative, and then the 4. So 9.6 second function EE negative 4 times 2.5 second function EE. And again, by doing that, that's like saying times 10 to the, and then negative 5. When you plug this in, I don't know if this is what your calculator gives you or if this is the rounded answer. I didn't write it if it was something different. But your rounded answer to 2 significant figures, which is how you need to have your answer reported because of those given to you, it would be 2.4 times 10 to the negative 8th. I'm going to let you go through this last one on your own. And the winning answer would be 3.75 times 10 to the 8th. All right, you got it through your first lesson in chemistry. Well done. Hopefully it all makes sense. Go and see a teacher if it doesn't, and good luck to you this year.